So the last session we started this topic, cosmology and astrophysics. Today we'll try to complete this last topic of Unit 5. And we were discussing how we can find the distance between the star or distance of the star from the Earth or galaxy. So we can use Kepler's law that we discussed in the last session. We can also use standard candle. So in a standard candle model, we'll assume that the star is having a known luminosity, and its luminosity is inversely proportional to the distance. Using this idea, we find the distance between the star and the Earth. We can also use a trigonometric parallax. Or we can use the Hubble's law to find the distance of the star. The Kepler and the standard candle we already discussed in the last session. Today we'll discuss the trigonometric parallax. So basically what happened in a trigonometric parallax, basically this technique can be used for nearby stars. The stars which are close to us, we can use this technique. For distant star, it's not valid. It's difficult to apply this technique. So how we use this or how we'll work out. A trigonometric parallax. So example, this is our sun. This is our sun. And we are at this position, at position A. The Earth is revolving around the sun. So we focus on one of the star for which we are finding a distance. For example, this is a star, but this is valid for nearby star. So we are finding this, the distance of this star. And what we will consider the background, the star back of this, which are known as the background star. The background star, they are moving, but we will consider them as stationary. Why? Because the distant stars are there, and according to trigonometric parallax, the object, like example, if you are at point A and you are observing two objects which are moving with the same speed, object 1 and object 2, but because object 1 is closer to you, so you will observe its uh, displacement. It appears that it is moving or covering a greater distance as compared to object 2. So objects which are nearby us and objects which are far away from us, if they are moving with the same speed, the objects which are far away from us, they can be considered as stationary, even though they are moving with the same speed than the nearby object. So the distant stars, these stars, they are also known as a background star. We'll consider them as stationary. We know the distance between the Earth and the Sun, that is 1 astronomical unit. So what we will do, like example, the first month, like in January, we are at this position. and we are looking at this star, observing this star with reference to the background star. So this one, and this is a star which we are observing. It will make a triangle. This distance is known. This is one astronomical unit, the distance between the sun and the earth. That is also the radius of the orbit of this earth. So after a 6 month period, the position of the earth will change as the earth is revolving around the sun. So it will be at a new position. So this is a new position of the earth. Angle, how we can work out the angle here? Basically, we are using a triangle, a trigonometric ratio, a right angle triangle. And in this case, our assumption is that the path, the distance between the sun and the earth, the average radius we are taking, because it is changing. It is not a spherical path or a circular path. It is elliptical. So these two distances are known. We know these two distances, which is the astronomical unit, one astronomical unit. So if I denote represent this by r, this also will be r, and we'll measure the angle again. Why we are measuring an angle after a duration of a 6 month? Because it will reduce the percentage error. As we know, the percentage error is the least count divided by value recorded multiplied by 100. We can do with this angle as well, but for accuracy, if we record a higher value, then the percentage error in this method or technique will be reduced. If we know the angle is theta and the distance between the sun and this star is d, after a 6 month period, the new position of the earth, and again we'll focus on this star and find the angle again. So what we will actually measure as the earth move, we'll get 2 theta. And so this in a 6 month duration, we'll get the value of a 2 theta. So if we need theta, theta is equals to x by 2. And what is x? X is the total angle which we measure. The reason why we are measuring for a duration of a 6 months, so that because this angle is very small and the percentage error will be much higher as the value is small. So duration of a 6 month will increase the angle. As it will increase the angle, it will reduce the percentage error. But again, there is a limitation. This cannot be used for distant star. Reason for that, the stars which are far away from us, the angle will be so small, then the percentage error will have a greater significant percentage error, which is difficult to find the accurate value of the, will make it error in the experimental value as well. So if we know the r, we know this d. So what we can do, we can find this d. How we can find this d? It's making a right angle triangle. This one is the hypotenuse for us, base, perpendicular. So we can use tangent theta. Tangent theta is perpendicular divided by base. So tangent theta is equals to perpendicular. What is perpendicular here? It's r. And what is base? Base is equals to d. Or r is already known, so d is equals to r divided by tangent theta. So what we'll get? We'll get the distance between the sun and the star. Is it clear? The trigonometric parallax. So basically, like in a January, the nearby star looks as they are in front of the other background stars, and in July, the nearby star look as though they are in front of other star. So basically, with reference to the distant star, we are finding this distance. So we using this, we can find a distance between the sun and the star, or we can find the distance between the earth and the star. Is it clear? So this is one technique, one way to measure how we are getting this theta. It's basically with reference to these stars, the angle subtended, like the change in the angle. Like, for example, these are the distant stars. Say star A is there and star B. And you're finding distance of this star. We can find a distance of this star from like between star, we can find a distance between star and earth, or star and sun as well. So here is the sun. So first what we'll do, when the star is in line with distant star B, we'll have one coordinate. And then exactly, like, we focus on the distant star A and B and the star which we are measuring. So after 6 month duration, after a 6 month period, it will be at a new position, and it will be in line with a distant star A. So we will measure this angle theta, and after knowing this angle theta, what we can do, we can divide into 2. That will be, or you can, instead of theta, you can say this angle is x, and then x will be divided by 2 to get value of theta. And using the value of the theta, you can find the distance between the star and earth, or star and sun. Is it clear? So trigonometric, basically this trigonometric measurement, it is used to find, like, measure the distance to a nearby star. We cannot use the stars which are far away from us. So as the earth is moving around the sun, and the relatively the closer star appear to move across to the background and more than distant star, and this is basically an optical illusion. And due to this optical illusion, we can use the technique to work out the distance between either the earth and the star, and or star and the sun. To determine the distance, using a trigonometric parallax, the star which we observe, or the star which we view, there should be a 6 month interval should be there, and the radius of the earth should be known, which is equal to 1 astronomical unit. Then how we can use the Hubble's law? How we can use the Hubble's law to find the distance between the earth and the star, or even the galaxy? Basically, according to the Hubble's law, it states that the recession velocity is directly proportional to the distance between the galaxies, or the distance between the star and the earth, or star and the, or galaxy and the earth. Or basically it's for galaxies, you can use the term galaxy. So higher or greater distance, like if cluster of galaxies, this is not one galaxy, like cluster of galaxies, and you have, in this region you have cluster of galaxies, and nearby there are other galaxies, example galaxy A and galaxy B. So when the data is collected for these galaxies, the galaxy which is according to Hubble's law, that the recession velocity, the speed at which the galaxy B is moving, is much higher as compared to galaxy A. So the galaxies which are far away from us are moving much faster or at a higher speed as compared to galaxies which are closer to us. So using this, the Hubble's law states that recession velocity is directly proportional to the distance between the galaxies. Greater distance between the two galaxies, they are moving much faster away from each other. And he used his result to plot a graph between the recession velocity and the distance for different galaxies. He's obtaining this data, but this data is more spread out. So as this data is more spread out, and when we say that two quantities are directly proportional to each other, so if two quantities are directly proportional to each other, it should be a straight line and it should pass through origin. So when he draw a straight line and he passes through origin, as two quantities are directly proportional, so their ratio should be constant. So the ratio of V, as V is proportional to D, or V divided by D, is equals to H naught. And what is H naught? H naught is known as the Hubble's constant. And this Hubble constant, how we can find the Hubble constant? By finding the gradient or the slope of this graph between the recession velocity and the distance between the galaxies, or the distance between the stellar objects, such as between two galaxies or two stars, and so on. So this is the data which he collect from different galaxies, and when he plot his result, the data is spread out. So as the data is spread out, he draw a best fit straight line, and this best fit straight line, because two quantities are directly proportional, so there should be a best fit straight line, and this best fit straight line, the slope is representing the Hubble's constant, denoted by H naught. So basically D is the distance between the point where we are observing the galaxy and to the galaxy. So how we can find this distance? So Hubble constant is there, so it is having a fixed value because it's a constant. And then how we can find the V? The value of the V, as he focused on these stars, the galaxies, what he observed most of the galaxies are giving redshift. Redshift means, like example, if you remember the Doppler effect, the relative change in frequency and the wavelength due to motion of source or observer, that relative shift in the frequency or the wavelength, that's called a Doppler shift. So to use this formula, because we have the formula V is equals to H naught D. H naught is a constant, that's we can know, or that's a known value according to the, but there is higher uncertainty is there. Why higher uncertainty in the value of H naught? Because the data of the galaxies and the distance, it's spread out, that's why greater uncertainty is there, as values are spread out. So we have the value of H naught, the Hubble constant, if we know, if we want the distance between the galaxy, or distance between the two galaxies, or distance between Earth and the different galaxies, so what we need v means the recession speed of that galaxy. So how we can find v? What he observed most of the galaxies which we are observing are giving redshift. What is the meaning of redshift? Means the wavelength what we should receive. Like example, if the composition, we know hydrogen is there, example, the hydrogen is there and it should give around 474 nanometer, the wavelength. But and we are at this position, we are observing this galaxy. But practically what happened, according to Doppler effect, if this galaxy is moving away from us, then what we will observe, a relative change in the wavelength or the frequency. The wavelength will become longer. So actually what we will receive will be longer as compared to what is emitted out. This is what is emitted, and we will receive a longer wavelength. So as we are receiving a longer wavelength, so we call that as a redshift. Most of the galaxies are giving redshift, that shows that they are moving away from each other. And this is also a conclusion, this is also give leads to a conclusion then, that we say a universe is expanding, because the most of these galaxies are giving a redshift. So 474 nanometer is a wavelength which is emitted out, example, from this galaxy. But what we are receiving longer than that. Like example, we are receiving 480 nanometer. So it shows that this galaxy is moving away from us. How we can find the speed at which this, or the recession speed at which this galaxy is moving away? So we can calculate a Doppler shift. What is a Doppler shift? Denoted by Z. So Doppler shift, which is denoted by Z, which is also equal to change in wavelength divided by original wavelength. Or using this Doppler shift, we can find the speed of the galaxy, the change in the wavelength divided by original wavelength, equal to the speed at which the galaxy is moving divided by the speed of the light, which is 3 exponent 8. So in short, we can say Doppler shift is equals to speed of the galaxy divided by speed of the light, speed at which the galaxies or the object is moving divided by speed of light. So we'll get a Doppler shift. So using this formula, what we can find, because c is the speed of light, which is uh, independent of all frame of reference, it's 3 exponent 8. Z is a Doppler shift. We can find like the original wavelength what we got, and the new wavelength using a change in wavelength divided by original wavelength. We can find a Doppler shift. Using a Doppler shift, we can find v, and after knowing v and h naught, we can find the distance between the Earth and the galaxy. Is it clear? The Hubble's law and how it can be used to find the distance between the Earth and different galaxies. But still, it's not 100% accurate. Why it is not 100% accurate? The reason is simple. The reason is because the uncertainty in the value of the Hubble constant, and it value, like, because the data is more spread out, that's why there is uncertainty. And the approximate value for the Hubble constant, it's about 70 kilometer per second per mega parsec. This will be the value of h naught. And the reciprocal of the Hubble constant will give us the age of the universe. How we'll get the age of the universe? As you can, How we'll know the age of the universe? According to Hubble's law, we know V is equals to h naught d. What is V? V is the speed, the recession speed. So using this recession speed of the galaxy, and the d is the distance of the galaxy from us. So speed, if speed is in meter per second, but normally like for galaxies it is in kilometer per second, and the distance, it is megaparsec. So when we divide kilometer over second divided by megaparsec, this megaparsec is because parsec is a unit of distance. So if I convert both of them into the same unit, like example, if I convert this kilometer into meter and I convert megaparsec into meter, so meter will cancel with meter. So what will be the unit of h naught if I have speed in meter per second and the distance, instead of megaparsec I have distance in meter? So h naught, the unit of h naught in that case will be 1 over second. So if I need a time period, it means if I take a reciprocal of Hubble's constant, what I will get? I will get the time period, or I will get the age of the universe. Still, the age of the universe, again, why the age of the universe? It's about 13.7 billion years. But again, there is uncertainty. And why it is uncertain? There is uncertainty in the age of the universe because of Hubble's constant value. As Hubble constant value, it is having uncertainty in it, that leads to uncertainty in age of the universe. Is it clear how we can use a Hubble constant to find the age of the universe? Then about the universe, we know very little about the universe. Why we know very little about the universe? Because, like example, the matter which required to hold these galaxies, to make these complex structures or formation of the star, like there is a galaxy. So when we find, because the galaxy means the matter is there, so when we find the value of the gravity to have this structure, and we find the amount of matter which is producing the gravity, like example, this is just an example, say to form this galaxy, this is just a crude example, it's not the exact number. To form this galaxy, the gravitational pull which is produced by this galaxy, it is about say 100 Newton per kilogram. This is just an example. But practically, when we find the mass, this is a calculated value. But practically, because whenever there is a mass, there is a gravity. The origin of the gravity is the mass. An object should have a matter. So when we find the amount of matter which can produce this 100 Newton per kilogram, we found that in practical, the matter which we know, it very small amount or less amount as compared to what the gravity is producing. So means there is some matter which we are not able to detect. The matter is there, but we are not able to detect. And what we call this matter, we call this as a dark matter. So known matter, the matter which we know, that matter is not able to produce this much gravity. So there is some extra matter should be there which is able to produce this gravity, which can keep this, the galaxy or the star can keep its shape or can form, and that matter is known as the dark matter. So when we compare the proportion of the known matter and the dark matter, the known matter is only 5% and the dark matter is about 25%. Then what about, because something should be 100%, so what about the remaining 70%? Remaining 70% is actually a dark energy. In the universe, the matter which we know is only 5% known matter is there, and rest like 95% we don't know, and rest 95% is actually 25% is a dark matter and 70% is a dark energy. What is the meaning of a dark matter and dark energy? So basically what we see now, that everything which we experience is a tiny fraction of reality. Like, because what we see now is only, or what we observe now is only 5%. 95% of the universe, the dark energy and dark matter we do not see. Like dark matter we are not able to see, and dark matter does not mean it's a black hole. So basically we have idea, we have theories, we have evidence that there is something, but we are not able to prove, or we are not able to identify, not instead of prove, we are not able to identify this dark matter. So basically dark matter is a stuff, you can say, which makes the galaxies. But so, and why we are able to conclude that, because when there is not enough normal matter which can produce the gravity, so it is there, but we are not able to detect this. And why we are not able to detect this dark matter? Because dark matter is not emitting out any electromagnetic radiation, it is not reflecting any electromagnetic radiation. So it is not emitting out electromagnetic radiation, it is not reflecting electromagnetic radiation, even it is not antimatter. Why it is not antimatter? Because if it was an antimatter, matter annihilate with antimatter, it release gamma photons, so we should able to detect. But it is not antimatter as well, even it's not a black hole. And same thing, what is the concept of the dark energy? Why we are making, why we are saying that there is dark energy? Energy means the some, like, work done or ability to do work or force applied to move the object, that's called energy. So what we observe that these galaxies, the particles in the space, they're continuously moving away from each other. So as they are continuously moving away from each other, it means there is something which is driving them, something which is pushing them. So the energy which is driving the particles, the space away from each other, that energy is known as the dark energy. And again, that this dark energy, we are not able to measure the dark energy and we are not able to detect this dark energy, but there are theories about the dark energy. Actually, about there are some theories about dark energy. Like example, this space, like between the two galaxies, there is a vacuum. So what is basically a dark energy? Dark energy means, this is just a theory, like it says that particle produce from nowhere and they annihilate and they transformed into another thing, an energy, and they push the galaxies, push the particle, or stretch the space. This is what they do. But this is still a theory. We are not able to detect this. We are not able to measure or detect this dark energy. But there is energy, there is some work done, because to move something, like I have an object, like if a book is there on the table, the book cannot move by itself until unless there is some energy. So there is some energy which is driving the galaxies. As we know, the universe is expanding. So if the universe is expanding, something should drive the galaxies away from each other, and that we called as a dark energy, the energy which is driving the galaxies from each other. So basically, what we can say that the empty space in the universe is forming more every second, and dark energy is an intrinsic property of empty space. Intrinsic property of empty space means whenever there is something vacuum, empty is there, means there is some energy, and we call that as dark energy. Is it clear the concept of known matter, dark matter, and dark energy? Dark matter is the matter which we are not able to identify, mm, detect, but that is responsible for the gravity, because gravity can only be produced by the matter. So that matter is known as the dark matter. And the energy which is moving the particles, moving the, expanding the space, expanding the universe, and that energy is known as the dark energy. Is it clear? The dark matter and the dark energy. So we started with the Kepler's and the Kepler's law and standard candle we already discussed in the last session. Trigonometric parallax, measuring a distance between the sun and the star, or star and earth. And Hubble's law can also be used to find the distance between the galaxies and earth, or star and earth. And according to Hubble's law, the recession speed is directly proportional to the distance between the galaxy and the Earth. The higher, like greater distance, moving at a higher speed. And using Hubble's law, Hubble's constant, we can find the age of the universe, which is about 13.7 billion years. But again, it's not accurate. Why it's not accurate? Because there is uncertainty in the Hubble's value. And collecting the data continuously, so until we have data more like greater values and more accurate answer for Hubble constant. And you can clearly see, it is obvious that the Hubble constant value will change. Why the Hubble constant value will change? Because if the universe is getting older, so means the time increase, so Hubble constant value should decrease. And then the concept of the dark matter, dark energy, and the known matter.